Thank you. So, I'm Dinusha Vatsalan, a postdoctoral research fellow in Peter Christen's research group at the Australian National University. So, we've been working on privacy preserving record linkage over several years, and in this talk, I'm going to present some of our research developments and outcomes in advanced techniques for privacy preserving linking of multiple large databases. So this is the outline of my talk. I'll first provide an overview of multi-party privacy preserving record linkage, and then I'll present some of our techniques developed for multi-party privacy preserving record linkage, and then I'll describe our novel data masking techniques based on Bloom filters for different data types. And finally, I'll conclude with an outlook to future research directions. So first let me start with a motivating example of why multi-party privacy preserving record linkage is required. So assume a demographer aims to investigate how mortgage stress affects people from different ethnic backgrounds and with different education and employment levels with regard to their mental and physical health. So this research will require data from various sources, for example from the health, social security and bank databases as shown here. Neither of these parties is likely willing or allowed by law to provide their databases to the researcher, but the researcher requires only access to some attributes of the records that are linked across these databases, for example the ones shown in black boxes. So since unique entity identifiers are not available in all these databases, we need to use some personal identifying attributes such as names, age or date of birth and postcode to conduct the actual linkage, which would then compromise privacy and confidentiality. So privacy preserving record linkage aims to overcome this problem by conducting linkage on the masked or encoded values of these personal identifying attributes to address the privacy challenge of record linkage, in addition to the two main challenges of scalability and linkage quality. So there have been various data masking techniques and privacy preserving record linkage techniques developed in the literature, and these techniques can be categorized into two groups, which are three-party protocols and two-party protocols. In three-party protocols, a linkage unit is used to conduct or facilitate the linkage of data sent by the database owners, while in two-party protocols only the two database owners participate in the linkage. So the advantage of two-party protocols over three-party protocols is that there is no risk of collusion between one of the two database owners and the linkage unit with the aim to learn about the other database owner's data. However, two-party protocols often require more complex or sophisticated techniques to make sure that the two database owners cannot infer any information from the data exchanged among them. Another categorization of privacy preserving record linkage techniques is whether they allow linking multiple sources or not. So known as multi-party privacy preserving record linkage, this incurs additional challenges in terms of scalability due to the exponential comparison space, and privacy due to the increasing risk of collusion between subsets of parties. So multi-party privacy preserving record linkage has received much attention in the recent times due to the increasing number of big data applications that require data to be integrated from multiple sources. So a family of private blocking techniques has been developed by Ranbaduge et al. To reduce the comparison space for multi-party privacy preserving record linkage. When coming to private matching and classification techniques for multi-party privacy preserving record linkage, all the existing techniques either support exact matching only, or they are applicable to categorical data only. For example, the exact matching protocol developed by Lai et al. Since approximate matching of string data is commonly required for privacy preserving linking of population databases, for example when we need to link using names and addresses, we aim to develop advanced techniques for approximate matching in multi-party privacy preserving record linkage. So our first technique is based on Bloom filters, and then we developed a counting Bloom filter based approach which improves privacy compared to Bloom filters, and then we developed an incremental clustering based approach that also allows identifying matching records between subsets of databases. So I'll next describe how these three techniques work. So in our first technique based on Bloom filters, we distribute the similarity calculation of P Bloom filters across P database owners. The dice coefficient similarity of P Bloom filters can be calculated as P into number of common 1 bits found in those P Bloom filters divided by the sum of 1 bits in each Bloom filter. So our idea is to split the Bloom filters into P segments such that each party processes a certain segment in the Bloom filter. For example, here we split Bloom filters of 9 bits long into 3. So the first party receives the first 3 bits from the other database owners. The second and third party receive the second 3 and last 3 bits from the other database owners, and then they apply a logical conjunction on these Bloom filter segments to calculate the number of common 1 bits in each segment. And once these values are calculated, a secure summation protocol can be used to securely sum the number of common 1 bits in each segment. And similarly, we can also apply a secure summation protocol to securely sum the number of 1 bits in each Bloom filter. And using these two sums, we can calculate the dice coefficient similarity of P Bloom filters. So this approach is quite efficient because the generation and processing of Bloom filters is fast and efficient, and the distribution and the calculation of similarity is distributed among the database owners. However, the number of comparisons required increases exponentially with the increasing number of databases, which is a common problem in multi-party privacy preserving record linkage. So in our second approach based on counting Bloom filters, we use a counting Bloom filter instead of P Bloom filters. So a counting Bloom filter is an integer vector which contains count values in the bit positions. So P Bloom filters can be summarized into a single counting Bloom filter by applying a secure summation operation. Given a single counting Bloom filter, we can calculate the similarity of P Bloom filters. For example, here we calculate the similarity of these 3 Bloom filters using its counting Bloom filter. How we do that? We can calculate like 3 into number of bit positions that have the value 3 in this counting Bloom filter divided by the sum of the values in the counting Bloom filter, and that gives the dice coefficient similarity of those P Bloom filters. So rather than sending Bloom filters to a linkage unit that can then calculate the similarity between Bloom filters, what we can do is we can apply a secure summation protocol where the linkage unit provides a random vector to the first party which can add its Bloom filter vector to the random vector and sends the sum vector to the second party, which then adds its Bloom filter vector with the sum vector and sends back. Sure. Yeah.
Can you go to your previous slide? So in this strategy, don't you run into do you run into a scaling problem here? So if you're multiplying by the constant 3 because of the number of instances, don't you run into a problem that not all of your columns here have the same possible distance? So like, don't you end up dictating towards things that are more full and right?
Actually the information gained from this counting Bloom filter is much less than if we receive a Bloom filter, right?
Well, it's not about an information leak. This is just about your distance calculation.
No,
I don't understand your scaling factor of 3.
3 is the number of databases. Now, if we compare two Bloom filters, we multiply by 2 because in the denominator we have all the sum of all 3, the number of 1 bits in all 3 Bloom filters.
Right, but not all of your filters have a max distance of 3, like all of your columns.
Yeah, if all Bloom filters are the same, we get a 1.0 similarity.
Right, but this 3 doesn't mean the same thing for each of these columns, is what I'm saying. It ends up giving more weight. It will increase distances for things that have less fill within that column. We can come back to this later.
Okay, yeah. So, so here, so using this, so by subtracting the random vector, we get a counting Bloom filter, and then the linkage unit calculates the similarity of these Bloom filters using the counting Bloom filter, and that gives a dice coefficient similarity, so that the linkage unit can classify the record pairs into matches and non-matches. The advantage of using counting Bloom filters over Bloom filters is that the information gained from P Bloom filters is much higher than the information gained from one single counting Bloom filter, because the counting Bloom filter only contains the sum values, not the individual bit values. And as I mentioned earlier, the computational complexity of multi-party privacy preserving record linkage is exponential with the number of databases. And this problem remains even when we use a private blocking or in filtering technique, as you can see from this table. However, most comparisons in record linkage are between true non-matches due to the class imbalance problem. And in order to identify a true matching set across all databases, it has to be a matching set between any subset of parties. So, by exploiting these two facts, we developed two improved communication patterns to reduce the comparison space further. So, our idea is to group parties into rings. So, in the sequential communication pattern, we only compare the matches from ring 1 with the candidate record sets in ring 2, and then the matches from ring 1 and ring 2 are then compared with the candidate record sets in ring 3, and we sequentially carry forward this process until we identify the matches from all rings. And similarly, in ring by ring communication, we again group parties into rings and identify matches from each ring by applying a secure summation protocol. And then in the second phase, we apply a secure summation protocol on the matches identified in each individual ring to identify matches from all rings. So, with these two communication patterns, we reduce the complexity of exponential growth with the number of databases P down to R, where R is the ring size. And before showing some experimental results, I'll describe our evaluation setting. So, we used North Carolina voter registration data sets for our experiments, and we extracted subsets of data sets for 3, 5, 7 and 10 parties, each containing up to 1 million records. We also used another set of North Carolina voter registration data sets of 26, each containing up to 5 million records, to conduct large-scale experiments. And these data sets include both non-corrupted and corrupted versions. We implemented all our prototypes using Python programming language, and we evaluated scalability using runtime, linkage quality using F-score, and we used our disclosure risk measures for evaluating privacy under the worst case assumption. So, here we present some results for the counting Bloom filter based approach. As you can see, the naive approach requires significantly larger number of comparisons for multi-party linkage compared to our improved communication patterns, sequential and RBR. and this makes the protocol scalable to linking multiple large databases. In the right hand side plot, we show the disclosure risk of counting Bloom filters and Bloom filters, and as you can see, the disclosure risk of counting Bloom filter is much lower than the disclosure risk of Bloom filters, which improves privacy of the protocol. However, a major drawback of these multi-party techniques is that they do not allow identifying matching records between subsets of databases. So we developed an incremental clustering based approach for large scale multi-party privacy preserving record linkage, which also allows to identify subsets of matching records. So in this approach, we apply clustering within databases, and then the clusters from each database are iteratively mapped and merged, such that at the end each cluster contains matching records representing a single entity. So this is an ongoing work, and here we present some initial results. This approach is quite efficient because it has a quadratic computation complexity compared to all the other multi-party techniques which have exponential complexity. Here we achieve linkage in quadratic computational complexity. So we also we were able to conduct linkage on 26 North Carolina voter registration data sets, each containing up to 5 million records, and we achieve reasonable linkage quality results as well. And here we compare our multi-party privacy preserving record linkage techniques with a state-of-the-art exact matching technique based on Bloom filters proposed by Lai et al. And as you can see, as we expected, the clustering based approach performs well by requiring lower runtime and achieving higher F-score. And as you can see, the exact matching approach proposed by Lai et al., which we denote as EMBF, performs well on the non-modified, non-corrupted data sets, but on the corrupted data set, all our approximate matching techniques outperform. And since the Bloom filter and counting Bloom filter provide same linkage quality results, we get overlapping lines for both Bloom filter and counting Bloom filter. So that's about our multi-party privacy preserving record linkage techniques, and next I will describe our novel data masking techniques based on Bloom filters for different data types. Bloom filters have been used for masking and matching string and categorical data, but no work has been done on masking and matching numerical data such as integer, floating point, and modulus data. So the problem of considering numerical data as strings and hash mapping into Bloom filters is that we lose the distances between actual values. For example, when we hash map integer values 29 and 30 into Bloom filters considering them as strings, we don't preserve the actual distances between them in the Bloom filter space. So our idea is like similar to hash map a set of q grams for a string value. Here we hash map a set of neighboring values for each numerical value that are within a specified interval and window size, and that would allow us to calculate approximate similarity between numerical values. Our results show that we get a monotonic relationship between the actual numerical similarity and the Bloom filter based similarity for different numerical data such as age, salary, and weight. We also developed a data masking technique for textual data recently by extracting representative words from a text based on their TF IDF weight and hash mapping them into a counting Bloom filter by setting the bit positions to a corresponding weight, and that would allow us to identify to calculate the approximate similarity between two text values. And that was our recent work, which was funded by Google Summer of Code, And we aim to develop more novel data masking techniques for other different data types as well. So to conclude, here we present the research gaps in privacy preserving record linkage literature based on an analysis using our taxonomy for privacy preserving record linkage. For the ones marked with solid outlines, some work has been done, and for the ones marked with dashed outlines, partial work has been done. But for the ones marked with dotted outlines, more research directions are required. For example, language for privacy preserving record linkage, big data frameworks, theoretical assessment, and privacy preserving record linkage for other adversary models require more research in those directions. So I'll conclude with this. If you have any questions, please let us know.
Questions?
So there's a whole body of research that's being done over at Stanford on by Dinusha Vatsalan's group on k-mers in Bloom filters and secure computation over genomic data.
Okay.
And I think it's almost exactly the same as your numerical Bloom filter.
Okay.
But I'm not saying it's bad. I just think that it looks like you might be converging onto the same solution, because this was actually a technique that was applied at a competition for secure genome comparison last year at University of California at San Diego.
Yeah, we've developed this for similar patient matching, because for medical data we need to match patients based on age, blood pressure, cholesterol level. So we developed a privacy preserving similar patient matching framework that includes all these different types of data masking functions, and that allows us to identify similar patients in a privacy preserving way. And I think Raina mentioned that they also have done some work on similar work on mapping geographical locations, right? Similar to numerical Bloom filters.
I'll just be curious to see what the relationship is.
Yeah.
They seem very similar.
Just speak.
Thanks for your talk. Could you click back to the sequential variations, please? Sorry, the one after. Oh, I see it. Thank you.
Okay.
Any other comments, questions? Yes.
Great talk. In that particular slide, I'd like to ask if the ordering of the rings affects the quality.
Sorry, the ordering.
Yes.
Yeah, actually, the linkage quality. I mean, if we are trying to identify subsets of matching, even for full sets of matching, the quality. I mean, the privacy risk and the linkage quality depends on the ordering of parties. So, for example, some parties may like to be grouped into the same ring in order to reduce the collusion risk, because they feel it's more secure to be grouped into the, because each ring uses a different encodings, so that a party from the second ring cannot infer any data about a party in the first ring. So depending on these privacy constraints, the parties can be grouped according to their preferences.
So are there any results of optimality here? Like, how do you decide that in practice?
So we just randomly group parties, like each ring has a same size, but in reality, each ring can have different sizes, but there should be a minimum ring size. Otherwise, there's no point of doing. It won't improve the. It won't reduce the comparison space. So in our experiments, we randomly group the parties. We haven't thought of any strategies how we can group parties yet.
Yes, please.
There is a slide on your counting Bloom filters and the random sequence that you're sending Can you go back there? Yeah, that one. Now, as I understand it, there's a natural limit to the amount of parties that you can have with this approach, right? Because if you have 9 parties, you're out of the game because the counting Bloom filter will reset, or is that not a problem?
No, it's not a problem. I mean, in terms of quality or privacy, it's not a problem. But if you increase the number of parties, the number of secure summation, in the secure summation, the number of steps will need to be increased. Otherwise, the complexity will go up. But we have proven in the paper that the similarity we get from a counting Bloom filter and P Bloom filters is the same.
Is that true even if it's, there's no problem there. The problem I'm referring to is, imagine this going on and on. What do you do? Can you still calculate the similarity even though you exceed the number 9 and then get back to 0? Doesn't that kind of distort the
So these are
similarity?
integers, right?
Just imagine counting more parties to that.
Yeah, but the counting Bloom filter contains integers.
Yeah.
So it can go beyond 9. That's not a problem.
Okay, so there's no problem. You can just...
Yeah, counting Bloom
okay.
filter is an
Yeah,
integer
alright.
vector. So in memory wise, compared to Bloom filter vector, counting Bloom filter takes more memory because it's an integer, while Bloom filter contains bit
Alright.
values.
Yeah.
But we have shown in the paper that when we increase the number of parties, that the memory increase is, compared to how we reduce the number of comparisons is less than the memory increase. So
Any other comments? Okay, thank you very much to our speakers.